It is still unclear how life got started, but it is known that the process of selection had to occur before the biology was established, so that selection built the framework. Chemistry is the thing that happens when electrons come together and form bonds. This order of emergence is necessary for the emergence of intelligence and consciousness. Selection can also precede bonds, depending on the environment. This allows me to be open to new ideas and run experiments in my head and in the real world. This helps me to stay grounded in science and discover new things. Biology amplifies this selection, and humanity and autonomous robots will supercharge it even further. This process can lead to the formation of more complex molecules and eventually life. Selection is often driven by energy barriers, catalysts, and the ability of molecules to interact with each other and redirect the causal chain. He was interested in how a Turing machine could build itself without a Turing machine, and this concept is known as a von Neumann constructor. There's about 18 million moles of water in the universe, which is about the same number of stars. Someone corrected me on Twitter when I said this. This is called an autocatalytic set, where A makes B and B helps make A and vice versa, forming a loop. This loop helps the molecules to grow out of the mess, even though it seems improbable. The ribosome is an incredibly complex object that was evolved over time and is responsible for every cell on Earth. Once we understand that selection can occur without the ribosome, but what the ribosome does is a phase transition in replication, we can understand how a watch could spontaneously emerge from a lineage of watches and cruder devices that are bootstrapped onto one another. He believes that the molecules we have in biology are contingent on the history of life on Earth, and that origin of life research should focus on finding life elsewhere. He also believes that ribosomes are a critical part of living organisms on Earth, as they are responsible for decoding and catalysis. This will help us to understand the origin of life, the likelihood of finding life elsewhere in the universe, and the future of humanity. Synthetic biologists have not been able to make a cell from scratch yet, as there is some contingent information embodied outside the genome in the cell. To do this, one would need to put inorganic and organic materials into a closed world, add energy, and wait for a life form to emerge. There are ways to ethically contain it, but it is still a risky endeavor. To experiment with the origin of life, one should use inorganic materials and look for evidence of replication and evolution over time. There are some groups doing this already, but they are using molecules that were already invented by biology. To know if the experiment is successful, one should look for evidence of replication and evolution over time. We should be cautious and aware of the potential dangers of messing with viruses and other life forms, as they can create a lot of problems if not done well. We are still far away from having to worry about the potential of something like Terminator coming to life, but we still need to be aware of the possibilities. Origin of life research is being done in good faith and we need to give it an open context to work in. This would help us understand ourselves, give us hope for alien civilizations, and potentially help us engineer a solution to climate change. If replicators from Mars were ejected and landed on Earth, then Earth would not have had to start life again. It is unlikely that life on Mars will be found, but if life is found in the outer solar system, such as on Titan, that would be very exciting. These states could be further divided into pre-conscious and post-conscious states, where we all meld into one super-intelligent conscious or some other weird thing that naturally happens over time. Some may be dead, some may be prebiotic, some may be living, and some may be technological. We need to start thinking statistically when it comes to looking for life in the universe. The Fermi paradox suggests that we may not be able to interact with other life forms because they are so different. I feel that the universe should be teeming with life, but the Fermi paradox makes me feel sad. We have to surprise ourselves and make non-biological life on Earth, and then people will say that we are part of the causal chain of that life. This gives us optimism that life is out there, but we have to remember that biology is only one solution and that the origin of life on Earth was contingent upon the chemistry available at the time. To find other Earth-like worlds, we should look for the same kind of rocky world in the same zone as Earth and expect to find biological-like stuff going on, but it won't be the same. It is difficult to define mathematically, but it is an important part of the human experience. Selection is a fundamental force in the universe, but it is uncertain how much variability and divergence there is in the emergence of life. It is likely that the emergence of elephants was wired into the history of Earth in some way, but it is also likely that the subset of things that are possible in the universe that are successful at creating elephants is very small. It is also difficult to say why we have not heard from aliens yet, but it is possible that they are far more advanced than us and are in contact with each other. We don't understand what life is, and this limits our ability to communicate with them. However, I think our innocence and lack of understanding can be interesting to them, and they may still want to teach us how to communicate. We would not be able to understand them, and they would not be able to understand us. However, there may be ways to interact with them, such as perturbing the system in interesting ways to see how they respond. On Earth, there are people who are curious and try to interact with other species, and this could be the same for aliens. We haven't interacted with aliens yet, but there is hope that we will in the future. We need to get smarter in order to decode their signal and qualify as intelligent life. There are a lot of people who believe in UFO sightings, which are sightings of weird phenomena that are not identified clearly at the time of sighting. I was disappointed with the recent political releases of classified information about UFOs. I don't want to discourage people from having these thoughts, but I don't think the evidence is enough to take it seriously. I do agree that some sightings could be an indication of something interesting, but I don't think everything can be explained away with sensor artifacts. I think we need more than just smartphones to capture interesting, relatively rare events. I also believe that anomaly detection in chemistry is important in order to understand anomalies, such as phlogiston and the ether. He has gone from suggesting space junk accelerating out of our solar system to interdimensional stuff in a short amount of time. We lack the technology and experimental design to capture these anomalies, but with the increasing number of detection systems, there is a chance that we may discover more. I also think that being disruptive and challenging people's ideas can be a good thing, as it can help us to learn and grow. I was also given the gift of being told I was stupid when I was young, which has made me strive to be smarter. We must be careful not to dismiss science because of this, but instead work with it to understand more about why we exist. We must also be aware that there are assholes in every space and walk of life, including science, and that these people should not be tolerated. No, I'm not aware of any alternate versions of me in other dimensions. The pickle heated up and exploded due to the water turning to steam. I now have an electronics workshop at home where I prototype experiments and suggest them to my research team. I also connect chemistry with computation, just like Rick from Rick and Morty. Assembly theory is a theory that states that if an object is able to be broken into many unsymmetrical parts, then it is likely that the object has been created by an evolutionary or information process. This theory is useful in recognizing life, as it can help to distinguish between random objects and those that have been created by an evolutionary process. The experiment was to determine the probability of complex molecules occurring by chance. NASA is sending mass spectrometers to Mars, Titan, and Europa, and the Dragonfly mission will be launching in a few years with a nuclear-powered mass spectrometer on board. The algorithm works by breaking down a molecule into its parts and then reassembling it in the minimum number of steps. This allows us to analyze the composition of molecules more quickly and efficiently than before. I use this theory to classify molecules and assign them an assembly index. I then tested this theory by cutting up molecules in a mass spectrometer and measuring the number of peaks. This showed that molecules with more asymmetry had more information and were more complex. It uses spectroscopic techniques such as NMR and infrared to measure the number of parts in a molecule and compare it to a threshold of 15. If the number of parts is above 15, it is likely that the molecule was produced by evolution. This allows us to create a scale of life and technology, and determine if something was produced by an informational process or not. It is a function of the complexity of the object and the number of copies of that object. Assembly allows us to understand the fact that not everything exists in the universe, and it can be used to measure the reusability of objects, not just for life and complex organisms, but for the universe as a whole. It is a computable problem that becomes hard very quickly, meaning it is difficult to figure out the minimum amount of reused components that will create a molecule. It can also be applied to cellular automata systems. It looks at the evidence of replication and selection in the system and assigns a higher assembly to more selected systems. It works by disassembling objects and understanding the steps to create them. It is determined by looking at the smallest reusable part, or atom, of a system. For molecules, the atom is the bond, while for objects like cars, it might be a small amount of iron or the smallest reusable part, such as a rivet or piece of plastic. In a microprocessor, the atoms might be transistors. The assembly index can be used to measure the complexity of life on Earth, with molecules of sufficient complexity indicating the presence of life, and molecules that require technology and microprocessors indicating the presence of technology. It is calculated by summing the number of copies of each molecule and dividing it by the assembly number of the molecule. This allows for comparison between different boxes, such as a box of sand and a box of molecules in a human body. It is based on the idea that life is able to create objects that are so complex that they cannot be formed in an environment with random interactions. This theory allows us to measure the evolution of life and its causal power, which can be seen in the ability to create artifacts and do things like launch rockets or build cars. Physics has a number of problems associated with it, and assembly theory is pushing them to reduce their belief system. This can be seen in the formulation of memory. I realized I could make a causal chain with the items in the box to assemble and create complex structures. When I saw it in molecules, I realized that the causal structure that emerges and the physics get stuck because physicists are allowed to suggest that we can go back in time. However, I don't think this makes sense because when I think of reversible phenomena, I have to borrow time from the universe to do that, which is impossible. Time is non-negotiable and cannot be stepped out of. I'm suggesting that physicists have almost got everything right, but there is a bit of dogma that needs to be challenged. Assembly theory appears to work without time being fundamental, but it is possible that the universe has many different ways of using time. Emergent time is when the universe is just doing its thing, assembly time is when the universe starts to write memories through bonds, and fundamental time is when time is assumed to be fundamental. People might get into trouble if they assume time is fundamental because they might not understand the origins of the memory that could be deeper. To understand this, we need to have a fundamental time, which allows us to have a deterministic universe that creates novelty. Time is fundamental and every event in the universe is unique in both space and time. We may not always get what we want, but if we try, we can get what we need, which is assembly theory. Assembly helps us understand weak emergence and allows us to crack open complexity in a new way. Examples of complexity include the Bernard instability, the formation of snowflakes, the emergence of a tropical storm, and the Mandelbrot set. It can be used to compare the complexity of molecules, microprocessors, text, music, and other systems. It explains why Nietzsche understood that we have limited freedom rather than radical freedom. This is similar to the game Dragon's Lair, which was a graphical adventure game with pre-recorded animation. The player had to time their movements correctly in order to progress through the game. Assembly theory gives hints about free will by showing that our past experiences and constraints limit what we can do in the future, but we can still use them to do amazing things. For example, we can look at how proteins and secondary metabolites will evolve over time to predict what opioids will look like in 1 billion years. They argue that even if we are in cages, we can still have a tiny bit of freedom. They then ask what the source of this freedom is and suggest that it could be something fundamental that allows us to feel free. Some people outsource their free will to their unconscious brain, while others try to overthink it. Sam Harris has realized that his conscious brain doesn't have free will, but his unconscious brain does. Through meditation, he has come to accept this fact and is now able to make decisions and accept them. This allows us to explore more of the state space and ask questions that we may not have asked before. I think that this is an interesting problem that the hard sciences don't understand, as it is related to the emergence of life, intelligence, consciousness, and free will. My feeling is that these are all the same problem, and that by exploring them we can add more fun to the world. People today don't understand how amazing it is to play with CA, changing the rules and initial conditions to see the patterns that emerge. We should create a TikTok account dedicated to putting out CA rules and see if it gets millions of views. The robots used a lookup table of experiments to do red, green, blue. They then had the robots compete in a game of hex, where the more blue the die, the higher chance it had to make the move it wanted on the hex board. They started to invent reactions that weren't on the list, and eventually had to be taken off Twitter. This inspired the idea of having a chemical entity that could communicate with the world, which is what the origin of life reaction is trying to do. Cellular automata, CA, are complex, but the complexity is baked in because of the boundary conditions and operations that have to be done to run the game of life in a CA. This complexity is interesting because it teaches us something about the origin of life. CAs and logistic equations are similar in that they both involve equations that can't be predicted, but the boundary conditions and the way the calculation is run can be important. We made a physical grid to demonstrate a chemical CA, which was the game of life. The paper explores the idea of using random perturbations or non-determinism to increase the complexity of the system. The encoding space for this is quite large and could lead to interesting results. It involves a chemical reaction between malonic acid and other chemicals that produces CO2 and acts as a battery to power the reaction. The reaction goes between red and blue and continuously needs to be fed in order to keep it going. It is an analog computer that can energy minimize quickly and can be used to solve complex problems. The researcher is exploring the possibility of creating a chemical computer that can solve optimization problems faster than a silicon computer, but is unsure of how big the grid has to be. They are created by humans and evolve by simple local rules. They can create arbitrarily complex and beautiful systems, which can give people a sense of mystery and awe. This complexity comes from the underlying digital computer, the von Neumann machine, and the Turing machine of digital error correction and states. Without these elements, the complexity of CAs would not be possible. However, I think it is important to recognize the power of the human mind in creating state transition machines and equations that are maximally compressed representations of reality. Physics, chemistry, and biology are all part of the same discipline, and the equations we find are a gift that can be shared with other civilizations. A state machine is an object, either abstract or mechanical, that can be used to perform a unit operation and switch it from one state to another. An example of a state machine is a turnstile. Computation is a process of building a state machine to make any molecule physically in the lab. This process removes the human from the equation and allows for a more uniform approach to making molecules. It involves labels and a transition diagram that can be used to programmatically create molecules. So I decided to create a chemical Turing machine, which would allow chemists to make molecules by following 4 abstract steps. I presented this idea to chemists, but they said it wouldn't work. I then went to an architecture conference and found people 3D printing shapes, which inspired me to think of 3D printing molecules. He designed the pumps and valves himself and used the power of the Ethernet to control them. He made the first version of the computer in 2016-17. This automation allowed organic chemists to become programmers without having to write long lines of code. This is what I have built a chemical programming language for, which is Turing complete and formally verifiable. This language can be used to read the literature and populate a state machine with primitives to program loops and create any molecule. The code is called ChI-DL and it can be used with a computer to act as a universal chemical reaction system. Just like the first computer, the ENIAC had 5 million soldered joints and 400,000 valves that were prone to exploding. chemistry has its own messiness. However, with advances in technology, it is becoming more reliable and efficient. Now, it is possible to make molecules on the computer that would take a human being a week to make in a fraction of the time. It is like a printing press for chemistry, and it can be used to make drugs and protect them from bad actors. It is a great way to make sure drugs don't go out of print. It is an XML-based language with for loops, conditional statements, and other features. It is named KaiDL after one of the team's students and postdocs. The language is designed to make it easier to write code for chemistry experiments, increase reliability, reduce ambiguity, lower costs, and increase safety. It also allows for the publication of executable chemical code. This allows chemists to access robotics for chemistry without the need for expensive, vendor-locked robots. It can also be used to generate other kinds of content, such as text, by forming deep representations of a particular space. This technology has the potential to increase access to data and make it easier to reproduce experiments, as well as create exciting and terrifying possibilities. It can generate syntactically and semantically correct programs, which can help with program synthesis. It can generate programs that operate on a computer, and a chemical analog of codecs has been developed which can generate context and run code automatically. To solve this, the software suggests the first go and then the chemist goes in and corrects it, as it is not safe for AI to generate code at this stage. It has its problems, but it is interesting and could be used to hack around with chemistry in the future. We are still in the middle of developing it, and have to be careful with safety issues. The possibilities of building a reliable universal computer are both positive and negative. Positively, it could enable drug discovery, supply chain stress, and more productive lab work. Negatively, it could be used to create dangerous substances like novichoks or explosives. To minimize the chance of the negative, we need to focus on protecting misuse and creating safeguards. They can also be used to create personalized drugs to treat specific conditions. However, computers can also be used for malicious purposes, such as the tragic incident of a pilot locking the door and setting the autopilot above the Alps. This could be done by encrypting KaiDLs so that they can only be used with the proper license. This way, it would be more difficult and expensive to reverse engineer the KaiDL than to just buy the regulated medicine. This system would allow for the cost of access to drugs to be lowered, and would also help to minimize the chance of drugs getting into the hands of those who would use them for harm. Additionally, this system would allow for the synthesis of molecules to be validated, and would also provide a fingerprint of the impurities that are carried across. However, there are risks associated with this technology, such as the potential for people to use it to manufacture illegal drugs or weapons. To mitigate these risks, Chemify is engaging in open discussions with society, investors, and those who will pay for the technology to ensure that the benefits outweigh the risks. It is also possible that recreational drugs could be manufactured with computers, but it is still far away from being a reality. In the short term, computers will help with molecular discovery and reliability, which will have a huge impact on the world. We should be excited about the potential of robots to automate engineering of nanomaterials, but also be aware of the potential for terrifying consequences. Assembly theory can help us fingerprint unknowns and reduce the chance of these consequences. Sarah Walker's team has been working on assembly theory and it could be useful for the nanomaterials project. The nano-robot would squirt a liquid with gold in it in a test tube and add reducing agents to make the gold. It outputs a KYDL code that can be used on any computer or qualified hardware to create nanoparticles with specific shapes and colors. We can engineer nanomaterial life forms, but the causal chain that will allow it is in the robot. We should be careful when dealing with these particles, as they could potentially produce something dangerous. Our number one kill switch is to always search for objects that don't exist in the environment. One way is to create a life bomb by focusing on atmospheres and chemical conditions of other planets and sending life forms there to see what kind of stuff they build up. This is a safe way to do large-scale experiments in a physical environment. This raises the question of what is human culture and how can we instill consciousness into other beings. An example of this is a robot lawnmower that has an electric field around the perimeter and chooses a random angle to rotate around and mow the lawn. Consciousness is something that is generated over a population of objects, including humans and robots. To create consciousness, a chemical system is best because it has access to many more states than a silicon system. It is possible that the larger number of states correlates to greater possibility of life, but constraints may also be essential. We should worry about algorithms written by humans on Twitter driving us insane and acting in odd ways. It is a mix of wit, intelligence, humor, knowledge, reasoning, emotional intelligence, and the ability to love, dream, and share those dreams. I think the biggest danger is not super intelligent beings, but rather dumb algorithms that are applied too broadly for selfish near-term interests. I'm optimistic that we are beginning to see this and that we can use social media for good, rather than for outrage. We are trying to improve the quality of life for the maximum number of people. Time is fundamental and the universe is not doomed to heat death. We are trying to figure out if we should send humans, robots, or a hybrid to Mars. People have their doubts about whether computation works, but I'm not qualified to answer that. Joska believes that the universe is a Turing machine, while Lee believes that the universe is not a Turing machine and that there is something more fundamental than Turing machines at the origin of life, intelligence, and the universe. Can the universe have Turing machines in it? Sure, they exist now. This means that energy, intelligence, and complexity may not be conserved, and this could have implications for the conservation laws that govern the universe. This would mean that the universe is intrinsically asymmetric and generates novelty, and that free will is effective. This would reduce the number of beliefs needed to understand the universe, as it would not require a magic order at the beginning or a second law. We believe that creativity is an infinite well and that the universe is constantly extracting every ounce of creativity it can. We also believe that humans are just one way of exploring creativity, and that there may be other meta-levels of exploration that we can't even imagine yet. We are beginning to explore the possibilities of free will and determinism, and I think we are converging on an understanding. We are also exploring the idea of a continuous to discrete transition in the universe, which could allow us to create Turing machines and other computing systems. Ultimately, I think there is something deeper at play that we are just beginning to uncover. He also mentioned Sarah Walker and Yeshua, two other fascinating people he has worked with. He hopes to have a conversation with all of us in the future. Otherwise you're just an inert chunk of randomly assembled molecules drifting wherever the universe blows you.